This is an Excel tutorial on numerical integration. I'm going to begin with a brief reminder on how we do exact integration, and I'm going to use the first order rate law as an example. And then I'll transition to numerical integration using examples of weather data. So imagine we're doing a reaction of A going to B, and that this is a first order reaction with a rate constant of 0.1, and the units on that are reciprocal seconds. So we could say that the rate of disappearance of A, negative dA dt, it would be equal to the appearance of B, positive dB dt, and that's equal to a rate constant K times A. So that's a standard first order rate expression, comes right out of the second semester of general chemistry. What we often want to do is to predict the concentration of A at time in the future, and we do that by the integration of this expression. So here's the log form of the integrated rate law, and here's the same expression written as an exponent. So I just went through and took the anti-log. So A at time t is equal to A0 e to the minus kt. So this is an example of a differential and its exact integral. And so if I want to do this in Excel, I have time in column B. I'll start with a concentration of 0.1, and I can predict the concentration in the future by saying A at time t is going to be equal to the concentration at time 0 times the exponent of negative k times t. And I'm going to clean up this reaction by putting a dollar sign in front of the C10. So on the Mac, I'm going to hold Apple T, and it puts dollar signs. And then the B11, C7 is the rate constant. Apple T on that. And if you're on a PC, you would use F4 to do this. The reason I put dollar signs in front of C10 and C7 is that those terms don't change. They're fixed in the spreadsheet. And I hit return, and now I can fill down. And you'll notice now I have that nice exponential first order decay that you would expect. And if we go down here, we'll see that, this is C dollar sign 10. Notice that's fixed. Exponent, C dollar sign 7, the rate constant, times the t, which is now 40 seconds. And if I want to finish this and calculate the concentration of B, well, from mass balance, I know that the concentration of B is equal to the amount of A I started with, and I'll fix that, minus the amount of A I have left over, and that's got to be B. And so I can come in here, and there's B. So there's an example of an exact numerical integration, and it's the example of a first order rate expression. We do this all the time in general chemistry, and of course the economists will say we do this all the time when we compute simple interest, and of course that is true. In the last example, we did an exact integration of a chemical reaction, a first order chemical reaction. In this example, we're going to use some field data from the roof of Kai's, and in this plot, I'm showing you the sunlight flux plotted as a function of date. So as the sun comes up, the flux, or the amount of light measured in micromoles per meter squared per second, so that's the number of photons in units of micromoles that hit the roof in a meter squared per second, and that's also referred to as a micro-Einstein per second. So the sunlight is plotted as a function of time, and we see the sun comes up and goes down and comes up and comes down, and this repeats itself every day. Some peaks are higher than others because this was a rainy or snowy day, and this was a bright blue sunny day. The challenge is, how do we calculate the total amount of photons that occurred over the month of January? We can't write an equation for this and integrate it. The expression would be way too complicated. So instead, we're going to take a simple finite difference approach. We're going to integrate by us taking little boxes, little rectangles, and adding them up over the entire course of the month. And our rectangle in this case is going to be 5 minutes long, because the sampling interval of our light sensor is 5 minutes. And the height of our rectangle is going to be the sunlight flux. And then I'm simply going to add up all the rectangles to get the total amount of light over the course of the month. So we'll start with 0, and we'll calculate the amount of light in the second rectangle. I'll zoom back to the right spot. And that's going to be equal to the time interval, 5 minutes, times 60, because there's 60 seconds in a minute, times the light flux, plus, because I want to add up all these rectangles, the rectangle that I started with. And now I'm simply going to fill down. And I've already pre-positioned the plot, so you can see the dark blue line is the integrated light flux over the entire month of January. So it starts at 0, and every time the sun comes up, it goes up, levels off, goes up, levels off, goes up, levels off, etc., all the way out till the end of the month. So it turns out the total photon flux in the month of January was 3.75 times 10 to the 8 photons. So let's turn that into some units that make any sense. I will set those two equal to each other. 3.75 times 10 to the 8 micromoles per meter squared of photons in the month of January. I happen to have the conversion of joules to micro-Einsteins. There's 0.219 joules per micro-Einstein at 500 nanometers in the middle of the visible spectrum. So I'll take this, and I will multiply. So the micro-Einsteins will cancel. My units will be in joules, and I end up getting 8.2 times 10 to the 7 joules per meter squared. That turns out to be the equivalent of shining a 30-watt light bulb on the roof of a meter squared area of the roof over the entire month. And that's about right for January in Maine. So this is the end of our example of a numerical integration, where we're simply adding up our observed values, little rectangles, summing the rectangles over the duration of our integration, and we're done.